Hello dear students, welcome you all. How is everyone? Okay, so let us start today's class. So in this session, in this series of sessions, we are discussing all the strength of materials questions, previous year's questions of engineering services examination. Okay, so this is lecture number 5 and we are discussing prelims PYQs. So this is first chapter, last topic. Today we will be discussing questions from ESE 2020 to 2023. Okay, so only 4 years papers are remaining, so there will be relatively less number of questions in today's class. So today's class will be over relatively in lesser time. Okay, and from tomorrow, from the next class will be on Saturday. So from Saturday we'll be starting next chapter, that is shear force diagram and bending moment diagram. Okay, so let us start with the first question. Today's first question: when a round bar material with diameter of 37.5 mm, length of 2.4 meter, so diameter is 37.5 mm, length is 2.4 meter, Young's modulus E is equal to 110 giganewton per meter square, and shear modulus G is 42 giganewton per meter square, is stretched for 2.5 mm, its bulk modulus will be. Now in order to calculate bulk modulus, what all things we need? Okay, so E is given, G is given, so these two elastic constants are given. So from these two elastic constants, can we find out the third elastic constant, bulk modulus K? Okay, when we know the value of E, when we know the value of G, can we calculate K, bulk modulus K? Okay, so we can calculate bulk modulus from these two. All the other information given is additional information that we don't need. Okay, so we have relation between E and G. E is equal to 2G 1 plus mu, and we have relationship between E and K. So E is equal to 3K 1 minus 2 mu. Okay, so from these two equations we have to eliminate mu. Okay, so let us calculate mu from here and put mu in this equation. Okay, so mu, E is known and G is known. Okay, from these two, E is how much? 110 is equal to 2 into G. Shear modulus is given as 42. Okay, into 1 minus 1 plus mu. Okay, so from here we can calculate mu. So mu will be equal to, just a minute, so 110, 50 by 42, 50 by 42, okay, minus 1. So mu is 0.19. From here we can calculate mu. Mu is 0.19. And when we have found mu, we can put mu in this equation and we can find out K. So K is equal to E upon 3, 1 minus 2 mu. So E is 110 divided by 3 into 1 minus 2 mu. 1 minus 2 into 0.19. Okay, so how much K will be getting? We'll be getting 110 divided by 3 into 1 minus 2 into 0.19. So it will be 59.14. 59.14. Okay, so no answer is matching. That means E is equal to 2G 1 plus mu. E is equal to 3K 1 minus 2 mu. 1 minus 2 mu. So E 110, here modulus 42. Okay, so 110 divided by 2 divided by 42, how much we are getting? 1.3. Okay, 1.3 we are getting. So this will be 0.31 actually, not 0.19, 0.31. 0.31. Mu is 0.31. So if I put 0.31 here, 0.31, so 110 divided by 3, 1 minus 2 into 0.31, we'll be getting 96.49. Yes, we are getting 96.49. 96.49 giganewton per meter square. Okay, so this will be the correct answer. So correct answer is option B. Option B is the correct answer. Okay. Okay, let's move on to the next question. A steel bar 2 meter long, 20 mm wide and 15 mm thick is subjected to a tensile load of 30 kilonewton. Poisson's ratio is 0.25 and Young's modulus is 200 gigapascal. So increase in volume will be, so increase in volume, volumetric strain. First let us write down the formula. Volumetric strain. Now here load is applied. So corresponding to stress we have to find out. So sigma x plus sigma y plus sigma z whole upon E into 1 minus 2 mu. This is the formula. Okay. So let us see what all things are given in the question. Okay. So 2 meter long, increase in volume. Okay. So increase in volume. First we will find out the volumetric strain, and then in this volumetric strain we will multiply it by the volume, actual volume of the material. Then we will get increase in volume. Okay. So first let us find out the volumetric strain. Okay. So from these given things, we can find out this given information will be used to calculate the volume. Okay. It is subjected to a tensile load of 30 kilonewton. So if it is applied, if tensile load is applied, that means only axial load is applied, only in x direction load is applied. So stress will come in x direction only. That means sigma y will be 0 and sigma z will be 0. These two will be 0. Poisson's ratio is given. Okay, Young's modulus is given. So from here we can find out volumetric strain is equal to sigma x will be how much? Force divided by area. Okay, so what is the force? 30 kilonewton. So 30 into 10 to the power 3. Converting into Newton, okay, divided by area. Cross-sectional area will be, it is 20 mm wide and 15 mm thick. So 20 into 15. Okay, so this is the stress in x direction divided by E. E is how much? Young's modulus is 200 gigapascal. 200 gigapascal, let us convert into megapascal. Megapascal means Newton per mm square. So if we convert gigapascal into megapascal, we have to multiply 10 to the power 3. Okay, so this is the 1 minus 2 into mu. What is the value of mu? Mu is 0.25. Okay. Now, so what is the volumetric strain? Volumetric strain 30 into 10 to the power 3 divided by 20 into 15 into 200 into 10 to the power 3 whole into 1 minus, okay, so 0.5, 1 by 4000. Volumetric strain is 1 by 4000. So what will be the change in volume? Change in volume will be equal to volumetric strain into volume. Okay, so volumetric strain is 1 by 4000. Okay, what is the volume? Volume will be 2 meter, length into area. So 2 meter, let us convert into mm. So 2000 into 20 into 15. Okay, so 10 into 15, it will be 150 mm cube. 150 mm cube. This is the change in volume. So change in volume, option B, 150 mm cube is the change in volume. Okay, clear? Next question. A punch of 20 mm diameter is used to punch a hole in 8 mm thick plate. Okay, so we are having a punch. Punch is like this. Okay, and this is a plate. Let me draw 3D 3D figure. So this is a plate, and in this plate we have to make a hole. Okay, a hole is to be punched in this plate. So if I put this plate here, okay, so there is a hole in between, and if I put this plate here and a punch, a rod type of arrangement is there. Okay, so this plate, let us say this is the plate. Okay, here arrangement is there, that is, it is a hole in here. Okay, and here is a solid rod. So what this solid rod will do, it will induce Okay, if I press this solid rod on this plate, what will happen? That there is a punch, there is a hole that will be created. Just a minute. Okay, so just imagine a rod, something like this. Okay, so this is the rod. Okay, and here in that area, in that portion, hollow part is there. Okay, so this part will be like this. Okay, this part will be like this. It will be pressed like this. Just a minute. Black color on black background is not visible that clearly, so let me take. Okay, so this is the rod, and if I push this rod, if I push this rod on this one, if I push this rod like this, then what will happen? In this part here, in this part, this much area, a shear stress will be created, and because of that shear stress, the hole will be punched. Okay, a hole will be punched, and this much part of the plate will get sheared away. Okay, so this will be the mechanism of the punch. So punch of 20 mm diameter is used to punch a hole in 8 mm thick plate. So this plate thickness is 8 mm. 8 mm is the thickness of the plate. If the force required to create a hole is 110 kilonewton, so here we have applied a force P. It is 110 kilonewton. Now this much force is required to create a hole in this plate. Okay, so the hole in the plate will be created corresponding to the diameter of this punch. Okay, whatever is the diameter, that much big hole is created. Okay, and that hole will be slipped from here. Okay, the average shear stress in the plate will be nearly, so 20 mm diameter. This is the diameter of punch. Okay, this is the thickness of the plate. Okay, so what is the shearing area? Average shear stress. Okay, so average shear stress, tau average shear stress will be equal to shear force. This total compressive force in this punch will be converted to shear force in the plate. Okay, so this much shear force will be applied on the plate. Shear force divided by shear area. Shear area. Now how much will be the shear area on this plate? Shear area will be pi d into thickness. Okay, pi d is the circumference of the circle. Pi d is the circumference of the circle, and t is the thickness of this plate. Okay, so average shear stress. What is the force? Force we have to calculate. So average shear stress is given. So force is given actually. Average shear stress is to be calculated. So force is 110 kilonewton. So 110 into 10 to the power 3 Newton. Okay, divided by shear area. Shear area is pi dt. Okay, so 110 into 10 to the power 3 Newton divided by pi. What is the diameter? Diameter is 20 mm diameter. 20 mm diameter into thickness of this plate 8 mm. Okay, so this is the area. So this question is very easy. The only thing that you need to understand is what will be the shear area. Okay, sometimes you might take pi d square by 4. So pi d square by 4 will not be the shear area. Pi d square by 4 will be the area of that part on which the compression force is applied. Okay, but shearing is happening not on pi d square by 4, but this part area, this area. Okay, on this area the shearing is occurring. Okay, so that will be the shear area. Now let us calculate this. So 110 into 10 to the power 3 divided by pi divided by 20 divided by 8. Let us calculate. So 110 into 10 to the power 3 divided by pi divided. So we are getting 218.83. 218.83 Newton per mm square. Okay, so this is the average shear stress. Average shear stress. Are you able to understand? So correct answer will be option C. Option C is the correct answer. Okay, let's move on to next question. A central steel rod 18 mm diameter passes through a copper sleeve with 24 mm inside and 39 mm outside diameter. So there is a central steel rod like this, okay, passes through a copper sleeve with 24 mm. So diameter of this is 18 mm, steel 18 mm diameter, and outside this steel rod is a copper sleeve. So copper sleeve is like this. Okay. So inside diameter of copper sleeve is 24 mm diameter, and outside diameter of copper sleeve is 39 mm diameter. 39 mm outside diameter. Okay. Now it is provided with nuts and washers at each end. Okay, so nuts and washers are provided at each end, and the nuts are tightened until a stress of 10 Newton per mm square is set up in the steel. So stress in steel is given 10 Newton per mm square. 10 Newton per mm square. This is the stress in steel. So if we tighten the nut, what will happen? If we tighten the nut, the steel will be having tensile load. Tensile stresses will be introduced in the steel, and compressive loads will be in the washer, okay, in the copper washer. So the arrangement is something like this. If we draw 2D figure, so this is the steel, okay, and this is the copper sleeve. This is the copper sleeve. Okay, so nuts are tightened. Okay, so when the nut will be tightened, the movement of nut will be like this, in this direction. Movement of nut will be in this direction. So when movement of nut is in this direction, it is pulling this steel tube like this. So when it is pulling the steel tube like this, it is pushing the copper sleeve like this. Okay, so there will be compression in copper and there will be tension in steel. Okay, now what to do? The stress in steel is 10 Newton per mm square, and stress developed in the copper tube, that is asked. This we have to find out. Okay, so now what we have to do, the total force developed in the steel will be equal to the total force developed in the copper. Okay, so forces in steel and copper will be equal to each other. Okay, so from this we can calculate stress in sleeve. Okay, so force in steel will be equal to force in copper. Okay, so stress in steel into area of steel will be equal to stress in copper into area of copper. Okay, so stress in steel is 10 Newton per mm square. Area of steel will be pi by 4 into, what is the diameter? 18 mm. So pi by 4 into 18 square, that will be equal to stress in copper into area of copper. Area of copper will be pi by 4. Outside diameter is 39, inside diameter is 24. So it will be 39 square minus 24 square. Okay, so from here we can calculate sigma c. Pi by 4 and pi by 4 will be cancelled out. Okay, so we will be getting 18 square into 10 divided by 39 square minus 24 square. So this we can calculate 18 square into 10 divided by 39 square minus 24 square, and this will be equal to 24 by 7, 3.428, 3.42 or 3.43 Newton per mm square. Okay, so this is the stress in copper. So correct answer is 3.4. 3.4 Newton per mm square. It is compressive. Correct answer will be option B. Okay, so in this steel will be having tensile stress, tensile, and here in copper we will be having compressive stress, right? Okay, let's move on to next question. 2-meter long alloy bar of 1500 mm square cross sectional area hangs vertically and has a collar securely fixed at its lower end. Okay, so 2-meter long alloy bar, a minute. So we are having a 2-meter long alloy bar like this. Okay, alloy bar of 1500 mm square cross sectional area hangs vertically. It is hanging vertically, and a collar is secured at the bottom. Collar is secured at the bottom. Okay, securely fitted at the lower end. What is the stress induced in the bar when a weight of 2 kilonewton falls from a height of 100 mm on the collar? Okay, so this is 2 meter long. This is 2 meter long, and from a height of 100 mm, from a height of 100 mm, a weight is dropped on this. Okay, so this height is just 100 mm. Just a minute. This is just 100 mm. Okay, so what is the weight? Weight of 2 kilonewton. So 2 kilonewton weight is dropped. Okay, so when it is dropped on this, what will happen? The potential energy will reduce and kinetic energy will increase. Okay, potential energy will keep on reducing and kinematic energy will keep on increasing until it hits this point. Okay, now when it will hit this point, when it will hit this lower collar, what will happen? That entire kinetic energy, all that potential energy that was converted into kinetic energy, and this kinetic energy will now reduce and it will be converted, it will be stored in the strain energy. This bar will keep on elongating. Okay, when it will hit this, then there is sudden applied stress on this, and because of that it will keep on increasing. Okay, so the length of this bar will increase, length of the bar will increase, and due to increase in the length of this bar, what will happen? It will store strain energy. So whatever was the entire potential energy here, that will be converted into the strain energy stored in the bar. Okay, now when it will elongate, after some time, what will happen? That this elongation will also stop. Okay, it will elongate to the maximum extent. Okay, let us say this elongation is delta. Okay, and at this maximum elongation, what will happen? The entire kinetic energy will also become zero. So entire potential energy converted into kinetic energy, and that kinetic energy converted into strain energy stored in the bar. Okay, so from conservation of energy, we can find that potential energy, initial potential energy that was here, potential energy of weight, potential energy of weight, that entire potential energy will be converted into the strain energy stored in this rod. Okay, so that will be equal to strain energy stored in the rod. Okay, now let us say this height is h. Okay, from h height this weight is dropped, and up till here the elongation is delta. Okay, so what is the potential energy of weight? Potential energy of weight is W into h plus delta, W into h plus delta. Okay, this is the potential energy, and that will be equal to strain energy stored in the rod. So strain energy will be equal to sigma square upon 2e into volume. Okay, so W into h plus delta, we have to calculate stress induced in the bar. So sigma we have to calculate. Okay, so W So the increase in the length, this can be ignored. Okay, increase in the length, this can be ignored because it is falling from what very small height. Okay, so the change in length will be very small. Okay, so when change in length will be very small, this can be ignored. It can be converted to 0. Okay, so WH will be equal to sigma square upon 2e into volume. Volume will be length, this length of the rod, into area of cross section area. Okay, so we can find sigma will be equal to WH into 2E upon LA, WH upon 2E WH into 2E. 2EWH upon LA. 2EWH upon LA under root. Okay, so from here we can calculate sigma. So 2 into Young's modulus. What is the value of Young's modulus? 120 gigapascal. 120 gigapascal. Let us convert into megapascal. So 120 into 10 to the power 3 megapascal. Weight is 2 kilonewton. Let us convert this weight into Newton only. So 2 into 10 to the power 3 Newton into H. What is the H? Height of drop. Okay, it is 100 mm. 100 mm divided by length of the rod. Length of the rod is 2 meter. So 2000 mm. 2000 mm. Area is 1500 mm square. So cross sectional area is 1500 mm square. Okay, so let us solve this. How much we are getting? 2 into 120. 2 into 120 into 10 to the power 3 into 2 into 10 to the power 3 into 100 whole upon 2000 into 1500 40 root 10, that means 126.49. 126.49 Newton per mm square. Okay, so stress is 126.49 Newton per mm square. 126.5. Okay, so correct answer will be option A. Option A is the correct answer. Clear? Let's move on to next question. The value of Poisson's ratio for brass material. Okay, so for brass material, it ranges from 0.31 to 0.34, something like that. Okay, so correct answer will be option C, 0.34. So for EAC examination, you have to remember the Poisson's ratio for various materials, for aluminium, for steel, for cast iron, for rubber, for cork. Okay, for all these materials, you must remember the Poisson's ratio, value of Poisson's ratio. For aluminium it is 0.33. For cast iron it is 0.2 to 0.25 or something about 0.25, 0.27. Okay, 0.25 or 0.27. Actually the options will be given in some range. Okay, not exact answer is not given in anywhere, means there will be some range, and that range will also vary from book to book. So you have to see the approximate range. From options you will be able to figure out what is the correct answer. Okay, for steel it will be 0.25 to 0.33. Okay, for rubber it will be 0.5. Okay, for cork it will be 0.1. Okay, so these are the values of Poisson's ratio for various material, and there are some more materials, okay, that I teach in the class, and you should remember these values. Okay, let's move on to the next question. A hole is to be punched through a steel plate of 8 mm. Okay, so similar question was asked, okay, earlier also. In today's class only we have done a similar question for shear stress. Okay, punch. Okay, so a hole is to be punched through a steel plate of 8 mm thickness. Okay, what is the least diameter of hole which can be punched if the steel punch can be worked to a compressive stress of 800 Newton per mm square? So this is the steel punch. Okay, here we will apply some force, and corresponding to this force there is some compressive stresses, sigma c, compressive stresses. Compressive stresses, maximum permissible compressive stress is 800 Newton per mm square. Okay, so when I apply force, okay, and here is my steel plate is like this, and in this steel plate I need to punch a hole. I need to punch a hole in this steel plate. So here when I punch the hole, this punch will come under compressive stress, compressive load will be there, and here it will be subjected to shear stress. Okay, so the maximum compressive stresses in this punch is 800 Newton per mm square, and the ultimate shear strength is 300 Newton per mm square. So here the ultimate shear strength is 300 Newton per mm square, tau max. Okay, so we have to find out the least diameter. Okay, what is the minimum diameter? that is required. Okay. So this thickness is 8 mm. 8 mm is the thickness. Okay. So force required to punch a hole in steel plate. Force required to punch hole in steel plate. So first let us calculate what is the force P required to punch a hole in the steel plate of diameter D. Okay, hole is of diameter D. For this diameter D, how much force is required corresponding to this shear stress, corresponding to the given shear stress. Okay, so force required will be equal to tau max into shear area, tau max into shear area. Okay, so now what will be the shear area? Tau max into shear area. Tau max is given as 300 Newton per mm square. 300 Newton per mm square. Let us write down tau max only for now. Okay, and what will be the shear area? This is the circumference into the thickness. Okay, so circumference is this pi d and thickness is t. So it will be pi d t. Okay, so tau max is 300 Newton per mm square into pi into diameter, we don't know, thickness is 8. Okay, so this is the force P required, P force. Okay, P force. Okay, now corresponding to this P force, the maximum stress here in this, the maximum compressive stress in punch should be 800 Newton per mm square. Okay, so force in force corresponding to maximum compressive stress in punch. Okay, so this force will be equal to maximum compressive stress into area, and here we will take cross sectional area. So maximum compressive stress is 800 Newton per mm square into area is pi by 4 d square. Okay, so now this force and this force, they both should be equal to each other. Now if we equate both of them, what we will be getting 800 into pi by 4 into d square will be equal to 300 into pi into d into 8, 300 into pi into d into 8. Okay, now 1d and 1d will be cancelled out, pi and pi will be cancelled out, 800 by 4, this will become 200. So 200 is equal to 300. So d will be equal to 3 8s are 24, 24 by 2, 24 by 2, that means 12 mm. So d is 12 mm. D is coming out to be 12 mm. Let us see options. Yes, correct answer option B. Option B will be the correct answer. We'll be getting 12 mm. Okay, let's move on to next question. Consider the following statements regarding the strain displacement. Okay, corresponding to strain displacement, two statements are given and we have to find out which statement is correct, which statement is not correct. Okay, the strain depends on the displacement of points within the body. Strain depends on the displacement of points within the body. Next, strain at points within the body not depend on the relative displacement of various points within the body. See, strain depends on the displacement of points within the body. This is the body. This is the body. Okay. Now, let us say this is the body. This is the body. And if I move this body from here to here, is there any strain happening in the body? If I move this body from here to here, all the points are having displacements. All the points are having displacements in this body. But all the points are having same displacement. So strain does not depend on absolute displacement. Strain depends on relative displacement. So even if I am moving this body like this, there is no strain, zero strain in this body. All the points are going displacements. So strain will not depend on the absolute displacement of the points. Strain will depend on relative displacement. What do we mean by relative displacement? If this is point A and this is point B, Okay, if point A and point B both are moving together, same distance, then there will be no strain. But relative displacement corresponding to A, if B is moving, then there will be strain. Okay, so if corresponding to point A, relative to point A, if point B is moving, that will be called as relative displacement. Okay, so if relative to point A, point B's movement is 0, whole of it is moving, then relative displacement is 0, strain is 0. But if there is some relative displacement, if I'm stretching it like this, so point A and B are moving away from each other, then there will be relative displacement between these 2 points, and then only strain will be occurring. Okay, so first statement, strain depends on the displacement of point within the body? No, it depends on the relative displacement. The strain at points within the body not depend on the relative displacement? No, it depends on the relative displacement. So both the statements are wrong. So correct answer will be option D, neither 1 nor 2. Okay. Next question. A flat bar 10 mm thick and 100 mm wide is subjected to a pull of 100 kilonewton. So this is a flat bar 10 mm thick, 100 mm wide. So thickness is 10 mm and width is 100 mm. Okay, subjected to a pull of 100 kilonewton. So we know the cross section 10 mm thick and 100 mm wide. Length is still not given, we'll see. Okay, so it is subjected to a pull of 100 kilonewton. So this is the force P applied, tensile force. One side of the bar is polished and lines are rolled on it to form a square of 50 mm side. Okay, so let us say this side is polished. Okay, and on this we have drawn some lines so that we have got a square of 50 mm side. Okay, so square of 50 mm side. So this side is also 50 mm, this side is also 50 mm. Okay, so 50 mm side. One diagonal of the square being along the middle line of the polished side. Okay, one diagonal of the square being along the middle line of the polished side. What is the change in the sides? Okay, so diagonal is like this, I think. Okay, so middle line of the polished side is like this and one of the diagonal is like this. Okay, now what is the change in the side? Okay, so here this is not the question of first chapter. This question will be done in principal stresses. Okay, this question is for principal stresses because angle of the diagonal is changed. Okay, so we will do this in fourth chapter. Fourth chapter is principal stress. Okay, so in chapter 4 we will do this question, principal stress. Okay, so let's move on to the next question. In a tensile test carried out in the laboratory on a steel specimen for 5 minutes. Okay, so we have taken a steel specimen, we have applied tension test for 5 minutes. Okay, the strain value noted at that time was 0.3. Okay, so strain value at the end of the test is 0.3. This is the strain value. What is the average strain rate of that steel specimen? So rate, average strain rate means the rate at which the strain is applied. Okay, so per unit time they have asked. So strain is this per unit second, per unit minute, per unit second, per unit minute. Okay, so it is done for 5 minutes. So strain rate, yani that means del epsilon by del t, rate of change of strain. Okay, so that will be total strain, change in strain. Initial strain was 0 and after test strain is 0.3. Okay, then time, how much time? For 5 minutes. Okay, so if I calculate the strain per unit minute, so I'll be getting 0.3 by 5. That means I'll be getting 0.06. So it will be 0.06 per minute. Okay, any option matching? 0.06? No. Okay, so we have to convert this into seconds. So 0.06 per 60 seconds. Okay, so 0.06 by 60, we'll be getting 1 by 1000. So 0.001 per second. 0.001 per second. Correct answer will be option C. Option C. Okay, so this is the strain rate. Let's move on to next question. A steel wire of cross-sectional area 100 mm square. So cross-sectional area of steel wire is 100 mm square. Length 100. Let us write here only. Length is 100 meter. 100 meter length is used to lift a weight of 2.5 kilonewton at its lowest end. Okay, so let us say this is the steel wire, and here a weight is 2.5 kilonewton. Weight of 2.5 kilonewton is hanging. Okay, so we are using the steel wire to lift this weight. What is the total elongation of the wire if the mass density of the wire is 8 kg per meter cube? Okay, so mass density of the wire is also given, and we are asked the elongation. So to elongation we will have to calculate elongation due to the load, that is external load acting on this wire, and elongation due to the self weight of the wire. Okay, so both the elongation we have to calculate and add. So total elongation will be equal to elongation due to external load plus elongation due to self weight. So delta external, due to external load, the formula is PL upon AE. What is the value of P? P or W is 2.5 kilonewton. 2.5 into 10 to the power 3. This is the load acting. Length of the wire is 100 meter. So let us convert this into mm. So 100 into 10 to the power 3 mm divided by cross sectional area is 100 mm square. 100 mm square, okay, is the cross sectional area. E is 200 gigapascal. Let us convert into megapascal. Megapascal means Newton per mm square. So 200 into 10 to the power 3. Okay, now let us calculate. First, let us count the zeros. 3, 4, 5, 6, 7, 8. 8 zeros here. 2, 3, 4, 4 and 3, 7. So 8 zeros here, 7 zeros here. So 25 by 2, it will be 12.5. Here we are getting 12.5 mm. Okay, then delta due to self weight, deflection due to self weight. Self weight deflection will be very less as compared to this due to external load. But anyhow, let us calculate. So it will be gamma L square upon 2E. What is the value of gamma? It is 8 kg per meter cube, gamma, and this is the rho, basically rho, and we have to multiply this acceleration due to gravity. Then we will be getting in gamma, okay, weight density. Okay, so 8 into 10, this is in Newton per meter cube. Okay, 8 into 10 into L square. What is the length? 100 meter. So 100 into 10 to the power 3, converting it into mm. So gamma L square upon 2 into Young's modulus. Young's modulus is 200 into 10 to the power 3. Okay. Okay, so now let us calculate 3, 4, 5, 5, 10. It is coming out to be even higher than that. Gamma L square upon 2E, length 100 meter. Very long wire. Okay, let us see how much we are getting. So here we are getting 11 zeros. It cannot happen. Gamma gamma L square upon 2E. Kg meter per second square. This will be in meter. So 80. Okay. Kg per meter cube. See, it is meter cube, no? Kg per meter cube. We have to convert this into mm cube. So this is Newton per meter cube, na? Newton per meter cube. We have to convert into mm cube. Okay. So we have to multiply 10 to the power 3 to 3. Okay. Now we will see. Okay. So here at the top we are getting 10, 11 zeros. Okay. So 2 into 10 to the power 11 here. And here we are getting 3, 4, 5 and 9. 9 and 5, 14. So 10 to the power 14. So it will be 2 into 10 to the power minus 3 mm. Okay. So if we add them, it will be approximately be 12.5 mm only. Okay. Elongation due to self weight can be neglected. It will be very, very less. Okay. So delta total will be equal to 12.5 and 002. 12.5002. So not 002, 12.502. 12.502 mm. Okay, so answer will be 12.5, but here none of the answer is matching. That means we have to mark the closest answer. Nearest answer is option A. Nearest answer is option A. Okay, clear? Next question. Statement 1. Tensile strength or ultimate strength is defined as the highest value of the engineering stress. Yes, this is true. True. When we draw the engineering curve, let us take an example of mild steel. Okay, so tensile strength, whatever we say that this is the strength of the material. Okay, so that strength is the ultimate strength, ultimate stress that it is able to withstand. That is the strength of the material. Okay, and it is the highest value of engineering stress. Now, for ductile materials, the tensile strength corresponds to the point at which necking starts. Okay, so for ductile material, this is the point where the necking will start. Okay, so this is the stress at which necking will start. So this is also correct. This is also true. Okay. So tensile strength is defined as the highest value of engineering stress. Yes, this is true, and this is also true. But is it explaining this? They are independently true, and this statement does not require any explanation also. No explanation is required for this. Na? Tensile strength, it is just a fact. It is just a fact. Okay, so for this fact, no explanation is required. So these are individually true, but it is not explaining it. Even explanation is not required. So correct answer will be option B. Option B is the correct answer. Okay, next question. Value of Poisson's ratio for cast iron. So cast iron Poisson's ratio is 0.2 to 0.25. Sometimes it will be written as 0.2 to 0.25, or sometimes it will be written as 0.2 to 0.27. Here 0.2 to 0.3 will be the most appropriate answer. Correct answer will be option B. Next question. A cylindrical bar of 25 mm diameter and 1.2 meter length is subjected to a longitudinal strain during a tensile test is 4 times the lateral strain. Okay. So here options are not given. Options are not given. Typist might have missed the options, but let us calculate anyhow. Okay. So what is the value of shear modulus? So first we can find out the Poisson's ratio. Poisson's ratio, longitudinal strain is 4 times the lateral strain. So when longitudinal strain is 4 times the lateral strain, we can say that Poisson's ratio is 1 by 4. Okay, so lateral strain divided by longitudinal strain will be equal to 1 by 4, and that will be Poisson's ratio. Okay, so Poisson's ratio we are getting as 0.25. So first thing that we have found out from this part is Poisson's ratio. Okay, so Poisson's ratio we have found out. Shear modulus we have to calculate. Shear modulus we have to calculate, and modulus of elasticity is given. Okay, so from these two we can find out the shear modulus. So we know the relationship E is equal to 2g 1 plus mu. E is equal to 2g 1 plus mu. From here we can calculate value of G. G will be equal to E upon 2 1 plus mu. So what is the value of E? E is 1.2 into 10 to the power 5. 1.2 into 10 to the power 5 divided by 2 into 1 plus mu. What is the value of mu? Shear modulus is 0.25. 0.25. Okay, so 1.2 into 10 to the power 5. 1.2 into 10 to the power 5 divided by 2 into 1.25, we will be getting 48,000. So 48,000 Newton per mm square. So according to option, we have to choose the answer. So maybe options will be 4.8 into 10 to the power 4. 4.8 into 10 to the power 4 Newton per mm square, or 0.48 into 10 to the power 5 Newton per mm square. So since options are not given, so we cannot verify, but out of these three, if any option is there, that option will be correct. Okay, let's move on to the next question. Which one of the following statements is not correct? Okay, for structural steel, the rupture strength is higher than the ultimate strength. For structural steel means mild steel. Structural steel is mild steel. So for structural steel, stress strain curve is drawn like this. Okay, what is the rupture strength? Rupture strength is here. This is the rupture strength. Rupture strength. This much is the rupture strength here. This is the rupture strength. So strength at which breaking will happen or fracture will happen or rupture will happen. So breaking strength or rupture strength or breaking, rupture or fracture strength, all are equal, same. Okay, then ultimate strength is this. This is the ultimate point and this is the ultimate strength. Okay, so here we are having rupture strength, this is the rupture strength and this is the breaking strength. Okay, so can you tell me which one is higher? Rupture strength is higher or breaking strength or ultimate strength is higher? This is the ultimate strength, this much, and this is the rupture strength. Which is more? So ultimate strength is more. So for structural steel, the rupture strength is higher than the ultimate strength. Wrong, it is incorrect. So we have to find out the statement that is not correct, and this first statement itself is wrong. Okay, so correct answer will be option A. Let's move on to the next question. A prismatic bar has a cross section of 25 mm into 50 mm and a length of 2 meter. So prismatic bar cross section area 25 mm into 50 mm and length of 2 meter, that means 2000 mm. It is subjected to an axial tensile force of 90 kilonewton. So axial tensile force 90 kilonewton. Okay, the bar is elongated by delta L. Change in length will be equal to 1.5 mm. What is the tensile stress? So tensile stress is load by area. What is the load? 90 kilonewton. So 90 into 10 to the power 3. It is the load divided by cross sectional area 25 into 50. 25 into 50. Easy. Let us calculate. Okay, so I am using calculator, but you don't have to use calculator because you need to give examination and you need to increase your calculation speed. So it is coming out to be 72 Newton per mm square. 72 Newton per mm square is the correct answer. So option D is the correct answer. Okay, let's move on to the next question. Next question, which one of the following statements is correct for an isotropic material? Okay, so isotropic material, shear modulus is independent of Young's modulus only. So for isotropic material, we are having 4 elastic constants. What are they? Shear modulus, Young's modulus, bulk modulus and Poisson's ratio. Okay, out of them 2 are independent and only 2 will be independent and remaining 2 can be found out. Okay, so shear modulus is independent of Young's modulus only. Shear modulus depends on Young's modulus. Okay, shear modulus is independent of Poisson's ratio. No, it depends on Poisson's ratio also. Shear modulus is independent of Young's modulus and Poisson's ratio. No, shear modulus is not independent of Young's modulus and Poisson's ratio. So shear modulus G is equal to E upon 2 1 plus mu. Okay, so shear modulus is depending on Young's modulus also and shear modulus depends on Poisson's ratio also. So it is not independent of Young's modulus and Poisson's ratio. So correct answer will be option D. So if Young's modulus will change, shear modulus will change. If Poisson's ratio changes, then also shear modulus will change. So it is not independent. Okay. Next, a body is loaded elastically so that strain in y direction epsilon y is 0. Epsilon y, strain in y direction is 0. Okay, this is given. And sigma z is 0. Okay, sigma z is also given 0. Very good. These two information is already given. Take sigma x and sigma y as finite. What is the meaning of finite? that it has some definite value. It is not very, very small that it can be ignored, and also it is not very large that it becomes infinite. So has some definite finite value, okay, that can be measured. What is the value of strain in z direction in terms of stress in x direction, Young's modulus E and Poisson's ratio mu? Okay, now here we will use generalized Hooke's law. What we have to calculate? We have to calculate what is the value of strain in z direction. So epsilon z we have to calculate. So epsilon z will be equal to sigma z upon E minus mu sigma x upon E minus mu sigma y upon E. This is generalized Hooke's law. Now if we use this generalized Hooke's law, and here sigma z is 0, sigma z, this is 0, okay, so epsilon z will be equal to minus mu by E sigma x minus sigma x plus sigma y. Okay, now here we have to find relationship between in terms of sigma x, mu and E only. We don't want sigma y here. Okay, so if we don't want sigma y here, we have to somehow eliminate this value of sigma y. So this can be eliminated by using this relationship, epsilon y is equal to 0. So when we know that epsilon y is equal to 0, we can use this relationship, sigma y by E minus mu sigma x by E minus mu sigma z by E. Okay, so now sigma z, we already know that sigma z is 0. So this term will become 0. Sigma x, we know it has some definite value, and strain in y is 0. So this E will come common, cancel out. Okay, so sigma y is equal to mu sigma x. We can write it like this, sigma y is equal to mu sigma x. So when we know sigma y is equal to mu sigma x, let us put in this equation. So epsilon z is equal to minus mu by E into sigma x plus mu sigma x. We'll be getting this. So minus mu sigma x will come common, minus mu by E 1 plus mu. Okay, so we'll be getting minus sigma x mu into 1 plus mu by E, minus mu sigma x minus mu sigma x 1 plus mu by E. Okay, so our answer will be option D. Option D will be the correct answer. Option D is the correct answer. Okay, let's move on to next question. What is the ratio of the elongation of a rectangular bar due to self weight? Okay, so we are having a rectangular bar and elongation due to self weight. So delta self is equal to gamma L square upon 2E is equal to gamma L square upon 2E. We can also write it as WL upon 2AE. WL upon 2AE. W, where W is weight of the bar. Weight okay, weight of the bar. Now what is the ratio of elongation of the rectangular bar due to self weight to the elongation if the total weight of the bar is applied at its end? Okay, so if I apply total weight of the bar W at its end, okay, this W I have applied at the end, so delta will be equal to WL upon AE, PL upon AE. Okay, so if I consider due to self weight will be WL upon 2AE, and if the same load weight of the bar is applied at the end, that means here we are not considering the self weight, we are just considering the whatever is the weight of the bar, that weight is applied just at the end of the bar, so we'll be getting WL upon AE. Okay, so what is the ratio? Ratio will be delta self divided by delta external load. It will be equal to WL upon 2AE divided by WL upon AE, that will be equal to 1 by 2. Okay, so delta self divided by delta external, it will be half. Correct answer will be option A. 1 by 2. Okay, so these were all the questions of first chapter. Okay, these were all the questions of first chapter. So from next class we will be starting all the questions of next chapter. Next chapter will be shear force and bending moment. So see you in the next chapter. Bye bye, take care.